Hi everyone, today we're going to be talking about the harmonic series and we're going to try to determine whether it diverges or it converges. So let me define for you what the harmonic sequence is. It's a sequence of numbers like this: 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and we just keep going like that so that we have the nth term being 1 over n. So this is the harmonic sequence. And as you can probably tell, 1 over n goes to 0 as n goes to infinity, because it just keeps getting smaller and smaller. If this is the number line, so we have 0 here, then we have 1, let's say this is 1, then 1/2 is here, then we have a third over here, and then we have a fourth over here, and it just keeps getting closer and closer to 0 as we have 1 over n. Now, a natural question to ask is, what about the sum? What do I mean by the sum? I mean the following thing: 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and we just keep going to infinity. What is the fate of that sum? Does it go to infinity or does it taper off? For example, it might taper off and be bounded above by some number, so we know that it converges. Or it might keep going to infinity. The answer is that it does go to infinity, but it does so at a very slow rate. And we're going to prove that today. We won't be talking about the rate itself, but we will show that it goes to infinity. So we have to understand what is meant by the sum first. What does it mean for there to be an infinite sum? What we're going to be doing is looking at partial sums. Let's say Pn is equal to 1 over 1 plus 1 over 2 plus 1 over 3 all the way through to 1 over n. This is a partial sum, because we've taken an initial segment of the series. And what we're going to show is that if we have the sequence of these, then this goes to infinity. Let's see what we can do in terms of estimating this using lower bounds. First of all, 1 over 1 is greater than 1 over 2. 1 over 1 plus 1 over 2 is greater than 1 over 2 plus 1 over 2. Let's go to the next power of 2, because things will be a bit easier that way. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Let's put this in parentheses. Then we duplicate what we have over here, which is 1 over 2 plus 1 over 2. And for this one, the estimate that we'll have is plus 1 over 4 plus 1 over 4. But notice that this is 1 over 2 plus 1 over 2 plus 2 times 1 over 4. And that's just equal to 1 over 2 plus 1 over 2 plus 1 over 2. Let's try going up to 1 over 8 now. We have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And now we're going to have 4 more terms. So 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. This is greater than 1 over 2 plus 1 over 2. we found that this is greater than 1 over 2. And this over here, we're going to show that we can estimate it as the following. We have 4 terms that are each greater than 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. You should be able to verify that yourself. And that is equal to 1 over 2 plus 1 over 2 plus 1 over 2 plus 4 times 1 over 8. And that is 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2. So we seem to have a sum of halves that keep going on forever. We have 1 half here. We have 2 halves here. We have 3 halves here. And we have 4 halves here. And it's reasonable to expect that this pattern will continue. What do I mean by the pattern? I mean the following. We expect that it'll be true. We haven't proven this yet, but we expect that it'll be true that the sum of 1 over k from k equals to 1 through 2 to the m is greater than, well, let's see, because we have a power 2 to the power of m here. So for 2 to the power of 1, we have 1 half. For, well, actually, this one is nothing. This is not quite a 2 to the power of 1. We just have 1 over 1 here. So it's actually 2 to the power of 0 leads to 1 of 1 half. In this case, we have a 2 to the power of 1, and 2 to the power of 1 leads to 2 of 1 half. In this case, the 1 over 4 is a 2 squared. So here we have 3 of 1 half. And finally, in this case, 8 is 2 to the power of 3. And over here we have 4 of 1 half. So what we expect is that there's going to be a sum of m plus 1 1/2, which is equal to m plus 1 over 2. Now we're going to prove this, but I want to tell you why this technique is going to work, because to be fair, the original limit that we had, it's for a general Pn that goes to the nth term, and that denominator is not necessarily a power of 2. By denominator, I mean this n. So the reason that this is going to work is that P of n, the nth partial sum, is less than a certain partial sum, which is a power of 2, and greater than the partial sum that is a power of 2 right below it. So if we can prove this, and this is equal to p to the power of m, then we're saying that this is greater than m plus 1 over 2. And what this means is that whatever the graph of Pn looks like, it's bounded below by this. And so if we have P of n is greater than m plus 1 over 2, and this goes to infinity, then P of n it also goes to infinity. Okay, so graphically it's like this. If our PNs are like this, and we know that there is a 1/2 here, and then we have 2 over 2 here, and then we have 3 over 2 here, and then we have 4 over 2 here, and it keeps going on, then no matter how slowly this grows, eventually it's going to get bigger and bigger and bigger. It won't necessarily grow exactly like that, but the point is that there is always an arbitrarily high number below it. Let me write that down. There is an arbitrarily large number below some Pn. And that means that Pn goes to infinity. So, okay, where were we? We need to prove this pattern. There are two components to this pattern. Now, what should be clear at this point is that we're going to be breaking things up into pieces. Like we have this piece here, and we have this piece here, then we have this block here, and we have another block here. And these blocks, there are two things we have to prove about these blocks. The fact that there are these blocks is clear enough. One, the terms of the block, let's say the block 1 over 2 to the k plus 1, comma 1 over 2 to the k plus 2, all the way through to 1 over 2 to the k plus 1. The terms of this block are each greater than 1 over 2 to the k plus 1, except the last one. The last one is greater than or equal to 1 over 2 to the k plus 1. In fact, it's equal, but we're going to need an inequality. And 2, there are 2 to the k terms here. We're going to have to prove these 2 points. And what this allows us to prove is that the sum of 1 over 2 to the k plus 1 plus 1 over 2 to the k plus 2 all the way through to 1 over 2 to the k plus 1, it's going to be greater than 2 to the k times 1 over 2 to the k plus 1, and that's going to equal to the half that we want. So it gives us just one more half into our sum. So let's prove this. It's not too hard to prove 1 and 2. First of all, let's say j is greater than or equal to 1. What we want is that 1 over 2 to the k plus j is greater than 1 over 2 to the k plus 1. And we're going to write this in a slightly different way, which is 2 to the k plus 2 to the k. And this is true if and only if 2 to the k plus 2 to the k, by clearing the denominators, is greater than 2 to the k plus j. And this is true if and only if 2 to the k is greater than j. Is that true over here? We're looking at this sequence here, so we want it to be true that j is less than 2 to the k. And yes, it is true, because we have 1, 2 all the way through to this one, which is 2 to the k plus 2 to the k. And the term before that is 2 to the k plus 2 to the k minus 1. And the next thing we want is that there are 2 to the k terms here. And that follows from the same decomposition that we have here, because we have the sequence 2 to the k plus 1, 2 to the k plus 2, all the way through to 2 to the k plus 2 to the k. And the number of terms here being counted using the second terms, 1, 2 through 2 to the k, and this has 2 to the k terms. Okay, so that takes care of that proof. Let me recap for you what we did. We started by defining the harmonic sequence, which we observed goes to 0 as the index n goes to 0. We then considered the sum, which is the harmonic sum, or the harmonic series. We then defined the partial sums of the harmonic series, and we hypothesized that the sums go to infinity. We computed lower bounds for some of these. So we have the 0th one here, the first one here, the second one here, and the third one here. We then hypothesized that it's bounded below by infinitely many halves, and that was our pattern over here. We then showed how bounding the partial sums whose index are powers of 2 also bounds below the general partial sum. And finally, we proved the pattern by first observing that we need to prove two things, one of which is that we can actually bound below the terms in a certain way, and the other part was that we need to find out the number of terms, and it needs to be 2 to the k terms. And we were able to prove both of those, which completes the proof. Okay, thank you for watching, and I'll see you next time.